Hi and welcome to Prototype. We'll be solving the problem for LeetCode 98, validate binary search tree. This is another problem in the LeetCode 75 study plan. Let's get to it. So given the root of a binary tree, determine if it is a valid binary search tree. A valid BST or binary search tree is defined as follows. The left subtree of a node contains only keys or values less than the node's key, and the right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtree must also be binary search trees. Okay, let's look at the example. We're given the binary tree with the root node 2 with left child 1 and right child 3. This is a valid binary search tree because the left value of 2 is smaller than 2 and the right value of 2 is larger than 2. Okay, second example, a binary tree with the root node 5 having left child 1 and right child 4, and 4 having left child 3 and right child 6. So here we can look at the right subtree starting at 4. 3 is smaller than 4 and 6 is larger than 4, so this part is valid. However, when we look at the subtree starting at 5, then it is not valid because 4 is smaller than 5, but it's on the right side, and that makes it invalid. Now I've made a couple more examples just to illustrate the point. Let's go over them as well. So let's look at this binary tree here, starting with root node 5 with left child 1, right child 6, and then 6 with left child 3 and right child 7. Now this one's a bit trickier because we can look at the subtree 156, and that is valid. And we can also look at the subtree 637, and that is also valid. However, again, when we look at the subtree starting at 5 on the right side, 6 is smaller than 5. And again, 3 is smaller than 6 and 7 is larger than 6. However, 3 is on the right side of 5 and 3 is smaller than 5. So this makes this an invalid binary search tree. Last case, we can just look at this slightly larger one that I've concocted here. Again, with the root node starting at 5, left child 1, right child 8, 8 having the children 6 and 9 respectively, and with child 6 having the right child 7 and 9 having the right child 18. This one is a valid binary search tree because let's look at 5. Every value to the right of 5, so every node in the subtree to the right of 5 is larger than 5. And then we can also look at subtree 8. Every value on the left side of 8 is also smaller than 8, and every value on the right side of 8 is also larger than 8. Okay, let's get to it. What do we have to do? Well, we will need to traverse the whole tree and see if we find anything that would make the binary tree an invalid binary search tree. Otherwise, if we traverse the whole tree and find nothing, then we return true. Okay, we will need some sort of storage mechanism. Let's just use a array, and we can actually let's use a queue, and we'll simulate it with an array. And we'll have a trusty while loop. The while loop condition will be while the queue is not empty. And in the queue, we will have a root. We will have the current node to be traversed, or to be visited, I should say. And we'll also need 2 more values. We will need a minimum value to compare to and a maximum value to compare to. And we will initialize this to negative and positive infinity. You could also use a maximum safe positive and negative integer. It doesn't really matter. Okay. And so what is the first thing that we will do in our while loop? We will dequeue this. So we will dequeue the current node, the minimum value, and the maximum value. And we can do that by calling shift on our array. And now we will have a condition. Basically, and if it fails this condition, then we will return false. What is the condition? Well, if the node value is less than or equal to the minimum, or if the node value is greater than or equal to the maximum, that would fail. Otherwise, if the left child exists, then we will add it to the queue. And we will also need to pass a minimum. Now, if it's the left side, the left side can be as small as it wants to be, but it has a limit with how large of a value it can be. So we pass through the minimum. Now think about this. If we start at the root 5 and the minimum starts at minus infinity, we visit 1 and there's no restriction on how small the left value is compared to 5. The only restriction for the left child is how large it can be relative to 5. It can't be larger than 5, and it can't even equal 5. It must be strictly smaller than 5. So it is the maximum value that we care about for the left child. So we pass the current node's value as the new maximum. And we will do the similar case for the right side. So pass the right value, and then we'll pass the current node's value for the minimum, and the maximum value we simply pass through. Okay, and if this all passes, then we will return true. Let's run it. And it passes the test cases. Let's submit. And this solution only beats 34.35%. How can we improve this? Well, there is no queue or native queue object in JavaScript. And this shift operation is linear on the sides of the elements. And it turns out actually we don't even need to use a queue. We can actually just replace it with a stack. Doesn't really matter. This would improve things just a little bit. Submit. And still slow. Okay, let's try it one more time. Just to check LeetCode. Okay, still slow. Okay, very well. So this is not the fastest method, but it is still a linear time complexity because we will visit every node exactly once. And in terms of space complexity, the widest size of the stack or array will be the widest level. So the level with the most nodes, that are not null. Okay, let's try a recursive solution. And in fact, the recursive solution will actually be faster. And the recursive solution will be very, very similar. Basically, we'll just be checking if the current node value is larger than the minimum value, and if the value is also smaller than the maximum value. What is the base case? Well, if the node does not exist, then we can just return true. We don't have to do any comparisons otherwise. And we will need a couple of values here. Let's say and actually we should do this in a function. So let's say is valid node. So then we'll have the node, we'll have the minimum value and the maximum value. There we go. And if the node does not exist, or if the node is null, then we can return true. Otherwise, if the node value is less than or equal to the minimum, or the node value is greater than or equal to the maximum, we return false. Otherwise, we return is valid node on the left child. So node.left. And again, if it's the left, then it can be as small as up to the current minimum. And otherwise, the right side will be restricted to the parent value. And we need to also check the right child. So we also call is valid node on the right child. And here the restriction is it must be larger than the current node's value, and then we pass through the current maximum. Finally, we can return is a valid node on the root node, and the initial minimum value, which is infinity, and then the initial maximum value, which is also positive infinity. Okay, run it and submit. Okay, so 82%. So it turns out the recursive solution is quite a bit faster there. It will also be a linear time complexity because we will visit every node exactly once. In terms of the call stack usage, it will also be the widest. It'll actually be slightly more because it will be the base, because the is valid node will also be called on null nodes as well. Okay, so that's the solution for validate binary search tree LeetCode 98. Subscribe to see more. We'll be doing the rest of the LeetCode 75 study plan questions in short order. Thank you and see you next time.